Hi and welcome back. Let's get started with some organic HL looking at the different mechanisms and substitution reactions. So today we're going to be looking at nucleophilic substitution reactions, and we will look at both Sn1 and Sn2 after we've had an introduction into our nucleophiles. So the types of organic reactions that we need to study in HL Chem include nucleophilic substitution, electrophilic addition, electrophilic substitution, and reduction reactions. Today we're going to concentrate on getting the mechanisms down for nucleophilic substitution. These are the reactions that you have seen already, i.e. where we have a halogenoalkane and we substitute with a strong base to form the alcohol. But in higher level chemistry, we have to understand the mechanism by which this occurs and be able to draw these mechanistic steps within an exam. So this gives us a brief path overall. So what we're looking at here is after we have a halogenoalkane, either from the addition across a double bond from an alkene or from the free radical substitution reaction of a halogenoalkane, we're looking at this reaction pathway here where we are adding in a strong base such as sodium hydroxide to form the alcohol. Just to review on mechanisms, remember that exactly how an organic reaction proceeds and in what stages is what we refer to as the reaction mechanism. Mechanisms show us exactly what is reacting and all the intermediate steps along the way to help us better understand the formation of intermediates, transition states, which would be slow points and fast points in our reaction. We use curly arrows to show the movement of electrons, of electron pairs. The arrow starts where the pair of electrons is and goes to where those electrons will move to. In this case, remembering that a double-headed arrow is showing us the movement of both electrons, therefore a heterolytic cleavage of the bond, whereas if we have a fishhook arrow, such as what we see for the start of our free radical mechanism, we have the movement of one electron. Okay, so this would be homolytic fission. And then if we had something like HCl, where these go to form H plus and Cl minus, both electrons have gone to the Cl, so we would have heterolytic fission in this case, forming the anion and the cation. Halogenoalkanes, we should remember, are alkanes with a halogen attached. These can be bromine, fluorine, or chlorine. They can even be iodine, but we tend to see a lack of polarity between these two. They have very similar polarity. So we see here that fluorine, of course, will give us the greatest dipole, then chlorine, and then bromine. We start to lose that polar nature of the bond by the time we're at iodine. So halogens are more electronegative, so the bond is polar, making the central carbon atom, i.e. the one that everything is attached to, slightly positively charged. So we refer to this as being electron deficient because the electronegative element is pulling the electrons away from this. We give it the delta positive. It's feeling electron deficient, whereas the halogen is going to be electron rich. Nucleophiles are reactants that contain a non-bonding electron pair or a negative charge. This high electron density will be attracted to a center of the positive charge, i.e. a nucleus, or an electron deficient center such as the carbon we were talking about on the previous slide. They're used in nucleophilic substitution reactions, so they will attack the halogenoalkane, okay, because our hydroxide is a strong nucleophile and will form an alcohol. This chart here gives us an idea of the nucleophilic strength. You'll see that iodide is a very strong nucleophile, and that our ammonia, chloride, fluoride, these are fair nucleophiles. Water is a weak nucleophile, as are alcohols. Our OH minus, our hydroxides, are very good nucleophiles, or good nucleophiles. So we need to remember this definition, that an electrophile is an electron-rich species attracted to electron-deficient parts of the molecule. So this means that we can have these reactions that we're talking about here, where chloromethane plus sodium hydroxide is going to give us methanol and sodium chloride, the salt, as a byproduct. This will occur with any of our halogenoalkanes, okay, remembering that we can have primary, secondary, and tertiary halogenoalkanes as well, and these will react differently based on the way that the halogenoalkanes behave. So nucleophilic substitution, by definition, this S is telling us it is a substitution reaction, that it is a nucleophile that is doing the substitution, and then we have two types, Sn1 and Sn2. So Sn is to signify substitution nucleophilic. Okay, the nucleophile is attracted and attacks the slightly positive electron deficient carbon atom, causing the carbon-halogen bond to break, and the halogen atom is released as a negative ion halide. We can show all this text simply by using a double-headed arrow, going from the making sure it starts at the negative or the lone pair of the nucleophile and goes to the electron deficient center. This pushes out the electrons of the bond between the carbon and the halogen, so they go up onto the halogen, producing the new bond between the R group and the nucleophile and pushing out the halide anion. Both shared electrons from the broken covalent bond are going to one product, so it's heterolytic, and the halogen is detached, and because it is leaving the main molecule, we refer to it as the leaving group. There are two different mechanisms, Sn1 and Sn2, and we need to be able to draw these and explain the process and the stereochemistry of each reaction type. The mechanism used depends on whether the halogenoalkane is primary, secondary, or tertiary. So in general, if we're doing a general reaction for a nucleophilic substitution, we're showing a generalized nucleophile, so it is element unknown X with a lone pair, negative charge, attacking the electron deficient center, and these electrons moving out onto the chlorine to give the chloride anion and the substituted product. So this is our general nucleophilic reactions, and next we'll start looking at the differences between Sn1 and Sn2.